Asha, this one, just a quick recap. We had talked about the types of chemical bonds. Okay, so the first thing was that I told you that elements, when you move to the right, they become more electronegative. Why? Because the elements on the right always have more protons, and when you move to the top, they become more electronegative because smaller atoms, they're less shielded, so they have a stronger attraction for electrons. So the tendency to gain electrons increases when you move towards this corner over here. So elements on the left, they like to lose electrons. They're referred to as metals. Elements on the right, they tend to gain electrons, and they're known as non-metals. So an ionic bond is going to be formed when you have a very large difference in electronegativity. What happens is that one of the elements is a non-metal, which is extremely electronegative. The other one is the least electronegative, which is a metal. So it ends up losing electrons from its outside shell, and the non-metal ends up gaining electrons. It forms a negative ion, this forms a positive ion, and as a result, you get an ionic bond, which is arranged in the form of a giant ionic lattice. So that's your giant ionic lattice, in which there's a regular arrangement of positive and negative ions. They would all be sticking to each other. They would all be attracted to each other. And the force of attraction is going to be an electrostatic force of attraction between positive and negative ions. And we talked about the strength of these ionic crystals. We talked about the fact that the strength of the ionic lattice depends on two things, and it depends on the charge. The higher the charge, the stronger the attraction. So if you have NaCl, the force of attraction is not that strong. But if you have MgO, Mg plus 2 and O minus 2, then the force of attraction is very, very strong. And the other one is smaller ions. Smaller ions are more tightly packed. They're more closely packed. So smaller ions are closer to each other, which also leads to more attraction. So together you can call this as charge density. Charge density is, for an ion, is you have greater charge on a smaller ion. So the charge is going to be a lot more, it's going to exert a lot more force. So ionic lattices, which have ions which have greater charge density, they are a lot stronger. So this is one thing that we discussed in the last class, and I told you about ionic compounds having high melting boiling points. Some of the ionic lattices can be really strong, depending on the charge density, and some of them are so strong, like MgO and Al2O3, that they are known as ceramics. They used in areas where extreme conditions are being used, like furnaces are made from MgO. Aluminium oxide is used to make all the high voltage transmission equipment, because any other thing would catch fire. You make it out of wood, it's going to catch fire. You make it out of plastic, the plastic is going to melt. The other thing about ionic lattices was that it was strong, but it was at the same time very brittle as well. They were very sensitive to the arrangement of the ions. So the ions are only going to attract each other if they're arranged in a very specific manner. The positive and negative ions must be together. So if your application of force shifts the lattice just a tiny bit by even a single atom, the negative ions would be together, the positive ions would be together, and that would result in a force of a repulsion. So that is where we had left off. And the other thing is, let's talk about the solubility and the electrical conductivity. So the first thing is ionic compounds. Ionic compounds, they conduct electricity when they're molten or aqueous. Why? Because then you have free moving charged particles. So ionic compounds, in solid state, the ions cannot move around. So ionic compounds conduct electricity when molten or aqueous. And when they conduct electricity, when they're molten or aqueous, why? Because they have free moving ions. So ionic compounds also dissolve somewhat, to varying extent. Some are very soluble, while others are very less soluble. So some are very soluble, while others have low solubility. So now in this case, let's discuss what happens when an ionic lattice dissolves. What happens is in an ionic lattice, let's say you have NaCl. So you've got Na+1, you've got Cl-1, and you're trying to dissolve. Now the lattice, the positive and negative ions are all sticking to each other. So they're very strongly attracted to each other. So you've got a positive ion, you've got a negative ion. The negative ion is attracted to a positive ion, and then the negative ion. Now, if I mix it in water, so think of the tiny salt crystal, like your normal table salt crystal, and I'm putting it in water. So when I vigorously stir this in water, what happens is that the ions, they scatter, they dissociate. So if I vigorously stir this in water, all the ions would get scattered. So this is something that's going to happen. The positive and negative ions would all dissociate. So the negative ion would break apart. Remember, you're vigorously stirring it with a spoon. So all the ions are dissociating. So here are all the positive and negative ions all getting scattered up. So this is what dissolving is. This is why the NaCl disappears. Like initially there's this tiny white crystal, but then when you stir it vigorously, all the ions, they just scatter in water and they completely mix with water. And the reason they're not able to get back together again is because there are lots and lots of water molecules that are coming in the way. So plenty of water molecules are going to prevent. So whenever you have a dilute solution, crystallization is not going to happen, or it's very rare that the ions would be able to get back together again, because there's so many water molecules that would keep the negative and positive ions away from each other. To crystallize or to form the crystal back again, you would have to get rid of the water molecules. That's why you evaporate. Crystallization happens once you reach a saturation point, which is you slowly evaporate the water molecules, and once they're gone, the negative and positive ions would start sticking together and they would start forming the crystal back again. Is that clear?
Yes, sir.
Okay, now the next question is, why are certain ionic compounds more soluble compared to the other ones? So remember, if you have a very strong ionic lattice, usually what happens is it all depends on the strength of the lattice. I mean, this crystal over here. If the lattice is very strong, then dissociation will not happen. The ions will not scatter in water by just it's not going to happen when you stir it with a spoon. Like marble is calcium carbonate. You stir it in water, no matter how long you stir it, there's going to be very little dissociation. The lattice will not break. So it all depends on the strength. Stronger lattices are usually less soluble. Are usually less soluble. Why? Because they're not going to dissociate. So you have a
Sir,
whole Haji.
sir, तो इनका charge density से कोई link है?
How? See, the strength of lattice is dependent on what? Charge density, right? The smaller the ion, well, it all depends on charge density. The smaller the ion and the greater the charge on it, the stronger would be the lattice that would be formed. Is that clear?
जी, sir.
So that is all about solubility. So this is all about ionic compounds. You've got ionic lattices. and we studied their properties. Now, the next thing that we're going to study is going to be about sigma and pi bonds. Now, ionic compounds was easy. One of them loses electrons, the other one ends up gaining electrons. So you need a difference in electronegativity. Now, what happens is, let's start talking about covalent molecules now. Now, when you have covalent molecules, so we're talking about simple covalent molecules now. Now, covalent molecules are going to be formed when there is going to be less difference in electronegativity. So the atoms will have lesser electronegativity difference. So when you have lesser electronegativity difference, that's when covalent molecules are going to be formed. So it's always going to be between non-metals. Now, in ionic compounds, you had one atom losing electrons, the other one gaining electrons. Now, in a covalent molecule, what will happen is both elements would be equally electronegative. So if I have a fluorine atom, now fluorine is one of the most electronegative atoms. So if I have one fluorine atom and I've got another fluorine atom, the two fluorine atoms are very electronegative. And fluorine has a total of, so it has a total of 7 electrons. And there's this other fluorine atom. Hanji.
सर तो इनके बीच लेस इलेक्ट्रोनेगेटिविटी डिफरेंस होगी नॉन मेटल्स के बीच में.
हाँ. But dono atoms in this case, right? I mean, the example that I'm doing, they have zero electronegativity difference. I mean, there's no electronegativity difference. They both are very electronegative, so they would try to gain electrons. So this is going to try and gain 1 electron, and this other one would also try to gain 1 electron. So now the issue is no one is willing to lose electrons. So what will happen is that this fluorine over here will try to pull the other fluorine's electron towards itself, while this fluorine over here will see the other fluorine's electron and try to pull it towards itself. Now, both of them are trying to pull the electrons with equal force. So what will happen is that the 2 electrons over here are going to be stuck in the middle. They're not going to go anywhere because, I mean, both atoms are equally trying to pull those electrons. So what will eventually happen is that these electrons over here would be shared. None of the fluorines, it's like 2 people fighting over these 2 electrons. So what is happening is that these electrons over here would be stuck in the middle. They neither would they go towards this fluorine or they would be gained by the other fluorine. Both fluorines are trying to pull the electrons equally. So the 2 electrons are going to be stuck right in the middle. This nucleus is trying to pull those electrons. This nucleus over here is also trying to, so this is trying to pull the electrons. This one is also trying to pull the electrons. And the 2 forces of attraction are going to get cancelled out. So the electrons would be right in the middle. So that's where the concept of sharing of electrons happens. When there is very less difference in electronegativity, the atoms, they would end up sharing electrons and the electrons would be stuck right in the middle. Is that clear? Amna, Mahad, Safar, is this clear? Hanji.
Yes, sir.
सर ये जहाँ पे इलेक्ट्रॉन फाइंड हो गए ये s ऑर्बिटल होगा.
नहीं, वो अभी हम डिस्कस करते हैं. I'm going to talk about orbitals next. ठीक है. So the first thing is the concept. Why do atoms? So there's this major difference. There are 2 types of chemical bonds. One is when there's a huge difference in electronegativity. So one atom simply loses electrons, and the other one, which is very electronegative, ends up gaining those electrons. So one forms a positive ion, the other one forms a negative ion. The other type of chemical bond is when you have two atoms and they don't have a difference in electronegativity, or the amount of electronegativity is very similar. So they're trying to gain those electrons, but they're trying to gain those electrons with equal force. So one is trying to pull over here, the other one is trying to pull over here. So the end result is that the electrons would be right in the middle. So these are known as simple covalent molecules. And the type of lattice that's going to be formed is going to be called a simple. I mean, the first thing is, let's talk about the properties. Generally, just let's talk about the properties. This is known as a simple molecular lattice. Or simple molecular structure. Now, what happens in a simple molecular structure is that you've got a fluorine molecule now. And they might ask you to describe, like, where's the chemical bond? So what's happening is that the shared electrons, or both nuclei of both atoms, so the nuclei of both atoms are attracted to the shared pair of electrons, which keeps both atoms together. The electrons in the middle, this fluorine nucleus is also attracted to it. This fluorine nucleus is also attracted to it. So which is why both atoms are sticking to these electrons in the middle. So nuclei of both atoms are attracted to the shared pair of electrons. To the shared pair of electrons. Now let's move back to the simple molecular structure. So what is a simple molecular structure and how is it different from an ionic structure? So you've got a fluorine molecule, and remember, it doesn't have any charge. There's no plus one, there's no minus one. No one ended up gaining electrons, no one ended up losing electrons. So here's another fluorine molecule, and it also has no charge, which means that the two fluorine molecules are not going to attract each other. So if you have one molecule and you have another molecule, the molecules will only have very weak intermolecular forces.
Sir? सर अब ये जो फ्लोरीन एटम्स के बीच में जो इलेक्ट्रॉन्स स्टक थे, क्या आप वहां से स्टार्ट कर सकते हैं? मेरा थोड़ा कनेक्शन का इशू आ गया था।
नहीं, मैं खाली एक्सप्लेन कर रहा था कि भाई वो इक्विवेलेंट बॉन्ड ना, शेयर्ड इलेक्ट्रॉन्स are getting attracted to both nuclei. Okay? So that's the force of attraction that keeps the two atoms together. You've got one nucleus over here, you've got another nucleus over here. They're both attracted to those two electrons. So which is why both, it's like one person over here is trying to pull those electrons, the other one is also trying to pull those electrons. So at the end of the day, both of them would be sticking together. Is that clear?
Yes, sir.
जो फ्लोरीन पे, दोनों फ्लोरीन्स पे जो मतलब नेगेटिव चार्ज था, जब उन लोगों ने मतलब शेयर कर लिया इलेक्ट्रॉन्स, तो मतलब उनका चार्ज खत्म हो गया, इसीलिए भी वो मॉलिक्यूल जो है एक दूसरे से बॉन्ड नहीं बनाते।
नहीं, they never had a negative charge to begin with. I mean, this was a neutral fluorine atom. It would have had a negative charge if it had gained that electron. So it's a neutral atom. This one is also a neutral atom. And no one ended up gaining those electrons. They're both still fighting over those electrons in the middle. So which is why.
So, but in the case of HCl, मतलब फिर तो चार्ज होगा ना, क्योंकि वो डिफरेंस हो जाएगा उनकी इलेक्ट्रोनेगेटिविटी में।
हाँ, अभी तो मैं बिल्कुल जनरल बात कर रहा हूँ, अभी हम उसमें स्पेसिफिकली आते हैं, अभी तो मैं बिल्कुल ब्रॉडली, अभी हम इसकी डीप डाइव करेंगे इसमें, ठीक है? तो वो, लेकिन वो हल्का सा चार्ज होगा, इट्स गोइंग टू बी स्लाइट पॉजिटिव, स्लाइट नेगेटिव, बट वील कम टू दैट, ठीक है? लेकिन ओवरऑल it's not plus one or minus one. I mean, there's no big charge on this, ठीक है? So which means the two molecules are not going to attract each other, and there's going to be very weak intermolecular force, force of attraction. That's going to exist, which is why most covalent molecules are going to have low melting and boiling points.
Sir?
हाँ जी.
Sir, किसके बीच में intermolecular force of attraction है? यहाँ पे आपने देखा weak intermolecular force of attraction किसके बीच में है ये? Between fluorine molecules?
हाँ, क्योंकि fluorine molecule neutral है ना. The other fluorine molecule is also neutral. So neutral को attract ही नहीं करता, तो बीच में there's going to be hardly any attraction. So which is why they're mostly gases. This would be flying around, this would be flying around. They wouldn't be stopping each other. Clear? So there's not going to be any electric conduction. Why? Because no charged particles, no free moving charged particles, electrons or ions. Ions or electrons. Anyway, so that's just generally speaking. So covalent molecules are going to have less difference of electronegativity, which is why the electrons would not be gained by either atom. The electrons would kind of be stuck in the middle, and which is why the molecule that's going to be formed is not going to be charged at all. It's not going to have any overall charge, which is why the molecules will not be attracting each other very strongly, and they would just have very weak intermolecular forces. And that is why covalent molecules usually have low melting and boiling points, and they have no electric conduction. They have no charged particles, no electrons, etc. To carry charge. So that is generally speaking. That's how covalent molecules are going to behave. So we've got ionic lattices. Ionic lattices are charged. They're made up of charged particles, which is why they're this big giant ionic lattices where there's a positive ion attracting a negative ion, which is then, and it just continues endlessly. Covalent molecules, they don't form this giant lattice. They just form these small, simple molecules that don't really attract each other, which is why they're mostly in liquid or state or gaseous state. I said, I'm moving on. Now we're going to start talking about covalent molecules in a lot more detail. Now we're going to talk about, yeah, clear. Is this clear up to this point? Safa, is this clear? Amna, Alicia, Aswa?
Sir?
हाँ जी.
सर थोड़ा सा वो प्रॉपर्टीज बता सकते हैं वहाँ पे क्या लिखा था वहाँ पे? अच्छा.
But low melting point and there's no electric conduction for covalent molecules.
Okay, sir.
And I'm specifically talking about simple covalent molecules. I mean, this is all about simple covalent molecules. This does not include graphite. Graphite is a giant covalent structure. We'll discuss that later. So now we're going to talk about the types of covalent bonds. Now we're going to do a deep dive into this. So the types. So the types of covalent bonds. So starting with number one, that's known as a sigma bonds. Now we're going to talk about the sharing of electrons at the orbital level. So the first one is sigma bonds. And there are many different types of sigma bonds. So even in sigma bonds, the first thing that we'll discuss is going to be an s orbital overlap. So remember, previously we had discussed that electrons don't, I mean, this is not a very good model of an atom. This is just a rough description of what an atom, or it's just a very overly simplistic description of what an atom looks like. So let's talk about sigma bonds. Let's talk about the S and S overlap and do this with an example. So I have an H2 molecule. So I've got an H2 molecule. Now in an H2 molecule, the simplistic diagram is that you've got two hydrogen atoms, and the two hydrogen atoms are kind of, I mean, they're exactly the same. You've got a nucleus in the center. This one has one electron, this one has one electron. They both try to gain each other's electrons. The end result is, because they're fighting over the same electrons, the electrons are kind of stuck in the middle. And that's what your covalent bond is. But now, an orbital level description. If you have a hydrogen atom, this is what a hydrogen atom looks like. It's got just one electron. So that means it's got an s orbital with 1 electron in it. And here's another hydrogen atom. It is exactly the same. Its electronic configuration is 1s1. So it's got an s orbital with 1 electron with exactly 1 electron in it. Now, when you have two of these s orbitals, so this is what hydrogen atom actually looks like. It's got a nucleus, and there's 1 electron that's buzzing around in a spherical region around the nucleus. In a spherical region, there's 1 electron, there's negative charge of 1 electron that's kind of located in a spherical region around the nucleus. So, I mean, so this circle represents the approximate area where that electron or the negative charge is going to be located. So there's this 1 electron that's buzzing around in a spherical region somewhere, the negative charge all distributed everywhere around the nucleus. And here's your second hydrogen atom, which is going to be exactly the same. It's 1s1 as well. So there's this other hydrogen atom, and it's got 1 electron that's buzzing around in that spherical region. So both atoms have this 1 electron that's buzzing around in the spherical region. But when they come close to each other, they would both try to pull each other's electrons. So there's going to be overlapping that's going to happen. What will happen is that you've got the 2 nuclei and they're fighting over those 2 electrons. Now the 2 electrons would kind of be found somewhere in this middle area over here, because both atoms are trying to pull those electrons. So the electrons and their negative charge is now going to be distributed somewhere in this middle area over here. And the 2 electrons are going, and the negative charge is going to merge. And you will have a single orbital now. That's going to be your sigma bonding orbital, because previously, remember, this orbital is the region, it's the area where there's a high probability of finding the electron. So previously the electron was buzzing around in a spherical region, the negative charge all distributed over here. This electron, its electron was buzzing around in this negative area. But when the 2 atoms started fighting over those electrons, the electrons are now stuck in the middle. The negative charge is now all distributed in this middle area over here. So the 2 electrons are now kind of mixed up. So the new boundary of the orbital is going to be this one. So the negative charge of the 2 electrons would be located somewhere in this area over here, specifically in this middle part. That will have the greatest probability of finding, I mean, that's where there's going to be greatest probability of the electron. So is this clear? This first example?
तो सर
हाँ जी,
जब इलेक्ट्रॉन्स आपस में शेयर होंगे तो एक s ऑर्बिटल अपने आप से ही मतलब एक ऑर्बिटल बन जाएगा जो जिसके अंदर दोनों इलेक्ट्रॉन्स होंगे.
हाँ, इसको I mean s orbital of 1 atom, and in hydrogen's case, hydrogen के पास s orbital है ना. It could be any orbital basically. ठीक है, any orbitals could merge up. So hydrogen has an s orbital, the other hydrogen atom also has an s orbital. So they would merge up and they would form this sigma bonding orbital. So this is no longer an s orbital. This is known as a sigma bonding orbital. And this is what your bond is. ठीक है, is this clear? So the reality is, ये जो हमने dot or cross बीच में बनाया था, in reality it kind of looks like this. ठीक है, all clear, everyone?
Yes, sir.
Okay, then the second one. So remember, it could be any orbitals that could merge with each other. So the second one is, let's do an S and P overlap. Remember, we're not going to study d orbitals. That's not part of our course, at least for AS. Now, part B is, let's talk about an S and P orbital overlap. So what happens? So what happens? And also remember that normal covalent bonds, sigma bonds or normal sigma bonds, Normally, it is the merging of two half-filled orbitals. Like the orbital has to be partially empty. Like if hydrogen had to, remember, if hydrogen had two electrons over here, then it wouldn't need electrons from the other atom because it already has a full I mean it doesn't have any room for further electrons. So the orbitals must be half filled, or they must be empty. There must be room for electrons. Like if it were to attract the other atom's electrons, then there must be space available over here. So the orbital must have one electron. If it has two electrons, then it can't really form normal sigma bonds. I mean, it can still bond in other ways. We'll study those. They're known as dative bonds. But the normal covalent bonds, normally they're formed when two half-filled orbitals overlap. So I've got this other molecule for it. Hanji.
और सर आपने कहा है कि ये सिग्मा बॉन्डिंग ऑर्बिटल होंगे, एस ऑर्बिटल तो नहीं होगा ना फिर?
कौन सा?
जो आपने मतलब हाइड्रोजन हाइड्रोजन का जो बनाया आपने,
हाँ,
ये सिग्मा बॉन्डिंग हो गया, एस ऑर्बिटल तो इसको नहीं कह सकते ना?
हाँ, ये तो सिग्मा बॉन्डिंग ऑर्बिटल है अब, क्योंकि अभी एस नहीं है, इट्स नो लॉन्गर एस. वो दोनों एस जो है ना वो मर्ज कर गए, उन्होंने ये बना दिया. ठीक है. So the next one is let's talk about the Hhf molecule. So now H has this electronic configuration 1s1. F fluorine has an electronic configuration of 1s2, 2s2, 2p6, sorry 2p5. If I expand 2p5, it's going to be 2px, 2py, and 2pz, and there's going to be two electrons, and there's going to be one electron. So what happens over here is that the 2p now if you look at this molecule, then F only needs electrons in this orbital. All the other ones are completely full. They don't need electrons. They already have two electrons. So F only needs electrons in this orbital, while hydrogen needs electrons in the 1s1. So it's going to be the overlap of these two orbitals. So I'm not going to draw the other orbitals because they're already full. They wouldn't be involved in bonding. They don't need any electrons. So I'm just going to draw, in hydrogen's case, there's going to be a spherical orbital, nucleus, and there's going to be exactly just one electron that would be buzzing around in this spherical region. And the negative charge of that electron is going to be everywhere in that region. And the other one is you'll have fluorine. Now in fluorine's case, you just have this p orbital, which needs electrons. So there's going to be, so there's going to be one electron that would be buzzing around in this dumbbell-shaped orbital. The negative charge would be spread around this axis. So that's your fluorine atom. I'm not drawing all the other, and that's my hydrogen atom. So I'm not drawing all the other orbitals because they're already full. So fluorine needs electrons in the p orbital over here. It needs one more electron over here. Hydrogen needs one electron in its spherical orbital over here. It still needs one electron. So they would start fighting over those electrons. Both will try to pull each other's electrons. And now what will happen is that the two electrons are going to get stuck in the middle. So the orbitals would merge. And this time, after the merger, it's going to look something similar to this. So it's going to look something similar to this. The two electrons would be stuck in this middle area over here. Their negative charge would be distributed mostly in this middle area over here. This is one of the, this is fluorine atom, this nucleus, and this is the hydrogen atom nucleus. The probability of the electron to go to the other side would decrease. This lobe would shrink. because I mean its electron, I mean previously where was the electron moving around? The electron was buzzing around in the entire, I mean it was buzzing around over here, it was also buzzing around in this area. But now because this hydrogen is pulling its electron, so the electron will kind of get pulled in this direction, and hydrogen electrons are going to get pulled in this direction. So that is where there's going to be the highest or maximum probability of finding the electron. The charge density is going to be very high over here. The chances of the electron going to the other side would be very, very low. So the two orbitals would merge, and that again is a sigma bonding orbital.
सर
हाँ जी,
सर इसका मतलब जब वो डायरेक्टली ओवरलैप करेंगे तो सिग्मा बॉन्डिंग होगा.
हाँ ठीक है, मैं प्रॉपर्टीज लिख लेता हूँ. And well, there's one type of orbital that's still left. I'll write the properties later. There's one type of orbital that's left, that's a PP overlap. Okay, so there's a third type. So remember, we're not going to talk about d orbitals. That's not part of your course. I mean, but remember, any orbitals could overlap. So the next one, option C, is a p orbital overlapping with another p orbital of another atom. Now, in this case, you will have a fluorine molecule, the one that we did earlier. So if you have two fluorine molecules, two fluorine atoms, remember, they both have the exact same electronic configuration. It's 1s2, 2s2, 2p. X2, 2p, Y2, all the other orbitals are completely full, and they just need one electron. Each one of them, they need one electron in the 2pz. That's it. So both fluorines are exactly the same. So in this case, what will happen is that there's going to be one fluorine atom, and it's going to have a p orbital with one electron in it. And there's going to be this other fluorine atom, and it's going to be exactly the same. So both fluorine atoms will have one electron. So both fluorine atoms will have a p orbital that needs, all the other orbitals are already full. So both fluorine atoms just need a p orbital that needs to be filled up. They would try pulling each other's electrons, and the electrons would be stuck in the middle area. So the two nucleus of the two atoms would be fighting over electrons, and the electron density would become greater in this middle area. It's going to shrink on this side, it's going to shrink on this side as well. So the maximum probability of finding those electrons would be right in the middle, and that's how your p and p orbital overlap would look like when two p orbitals merge. So all you have to remember now is that there is a sigma bond. It's the same covalent bond. Sometimes between atoms, the s orbital overlaps with the s orbital. Sometimes what happens is that the s overlaps with the p of the other atom. The electrons are still stuck in the middle. And sometimes what happens is that the p orbital of one atom overlaps with the p orbital of the other atom, and the electrons are kind of stuck in the middle. So that is your three types of sigma bonds. They're all exactly the same. It's just that the shapes are different because the orbitals that are overlapping are different. So you have to remember this. And you have to be good with shapes. They'll specifically ask you to draw any one of them. They're not going to give you very complicated molecules, just simple ones, but make sure you know how to draw a P and P overlap, an S and P overlap, and an S and S overlap. Okay, is this clear, everyone?
Yes,
Yes,
sir.
sir.
So okay, let's continue tomorrow. I'll talk more about this. I'll do a few examples of more complicated molecules, like a water molecule, and we'll discuss. So you should be able to identify whether it's a POP overlap, SOP overlap, or an SNS overlap. But we'll talk in detail about this. I mean, this is all that you have to know, but we'll just do a bit more just in case. But we'll do that tomorrow then, okay? Okay, everyone.
Sir,
Haji.
सर इसके अंदर तो मतलब कोई डेफिनेशन ऐसा नहीं है, सिर्फ मतलब कॉन्सेप्ट होना चाहिए शेप्स का, और जिस तरह से
हाँ
बॉन्डिंग हो।
वो ड्राइंग पूछेगा ना कि ड्रॉ, वो कहेगा H2 मॉलिक्यूल में सिग्मा बॉन्ड ड्रॉ कर दो, ये HF molecule में draw the sigma bond, so it's going to be this one, or FF molecule draw the sigma bond, so it's going to be this one. ठीक है, सिग्मा बॉन्ड की कुछ बातें वो भी मैं लिखवाऊंगा, ठीक है, मुझे याद भी करा देना उसकी
सर उसकी प्रॉपर्टीज,
मतलब इसकी डिस्क्रिप्शन के व्हाट इज अ सिग्मा बॉन्ड, ठीक है, मतलब वो नजर तो आ
ओके
रहा
सर।
है लेकिन उसको वर्ड्स में हम लिख लेंगे, ठीक है। तो ठीक है, लेट्स कंटिन्यू टुमारो। ओके, अल्लाह हाफिज।